Okay, so for some reason it crashed when I was recording previously, so there's going to have to be a second video here to cover the next half. Okay, so we want to draw an SM chart where there's an input X and output Z. It must prevent this from occurring. Resets after target. Example input is this. So let's do it from scratch again. I just felt like that's just better. Let's store this down here in case we mess it up. But okay. So when we start, we have nothing. If X is 1, we're going to go to the next state, and our output Z is going to have to be 1 because it follows, it equals X. If we get a 1 again, and then if we're in that first state S0 and we get 0, that's nothing. And there's no output. You could specify Z equals 0 if you want, but usually when it's 0, we just leave it like this. Okay, so we have a first 1. If we get a 0, we go here, and the output Z is 0, so we don't put anything in the link. We could do Z equals 0, but it's just not. We get a 1, well, then we just go back to here. So we're in our final state. We get a 1. Get a 1. Then we go back to 0 because it resets. And then there's no output Z in the link because we want it to be 0. We get a 0. We I think it resets too. Okay, we don't even need that because regardless, it's going to reset. So yeah. Yeah, it's pretty similar to it. Okay. So that is that. Just go through it. So, oh yeah, and then the way you encode the states is 0, 0, 0, 1, 1, 0. And the reason why it's just A and B instead of A, B, C is because there's 3 flip-flops, and you can represent up to 3 with just 2 bits. Okay. So yeah, let's go through this output. So Start off with nothing. X is 1. Let's do the state. Starts off with this. We're in state 0. We get a 1. State 0. Get a 1 from there. So then we go to S1. And Z is outputted as a 1. Okay, so we're in S1. We get a 1 right here. Well, we go back to S1, and Z's outputted 1 again, so 1. Okay, we're at S1. We go to 0. We go to S2. Nothing in the link, so Z is 0 right there. State 2. X is a 1. So regardless of whether or not X is a 1, it's going to be 0 and it's going to reset. So it goes back to state 0. We get a 0 again, so still in state 0, state 1, state 1. And state 2, 0, 1, and yeah, that's how you do that. So in your test, you're going to have a problem very similar to this. Okay, the final thing that you have to worry about is this kind of problem. So you're going to be given a flip-flop, might be a JK, might be something else, and you're going to be given a timing diagram, and you're going to have to fill out what Q is going to be. So you need to get the truth table, and for this flip-flop, this is the corresponding truth table because there's nothing different about it. Yeah. So in here, it's active high rising edge clock. That's why on this side of the rectangles on CLC, on the front part of it, on the rising edge of the clock, it triggers. But if there was a dot right here, like a little bubble, then it would be here. But that's not this case. So, oh, and there's a propagation delay. Well, we'll get to that. So for the first one, J and K are 0 and clear is not relevant. Let's start with the clear. So clear, whenever clear is 1, Q is 0 no matter what. So for here, it's just going to be 0. And let's represent this as the propagation delay. Zero. Because this right here goes down. This is the first rising clock edge that it sees clear. So immediately it goes to 0. So that's that. Start J and K 0, 0. So according to the truth table, when 0, 0, no change in state. So if it started off 0, it's going to stay 0. Even here, it's 1, 0. So when j is 1, so when j is 1, and k is 0, it sets q to 1. So and then the next one's 1, 1. Okay. So when they're both 1, it toggles. So it's going to go to 0. Then here, 0, 1. So it's 0, 1. I mean, j is 0 and k is 1. And the resets q is 0. Okay, so it just stays 0. Get 1 to 1. Okay, so then it stays 0 for the whole thing. And this would be the waveform of that. And this is the propagation delay. Now in your test, there's going to be little increments along the axis. He's going to tell you, like, let's say this is, and he's going to tell you what the delay is. Hold on. Yeah, so you're going to have something like this. And whatever propagation delay after the rising edge of the clock, which it's going to be marked on your exam where it is with the dotted line. So after that, you only reflect the change that happens because of these two. This distance from the line marking the rising or falling edge of the clock. So yeah. And also one thing to look out for is, let me see, on your test, if there's a bubble here, well then that means that clear is going to be active when during this entire time instead of this time if there's a bubble there. Because that means it clears when it's low. So yeah. And there's that. Let me see if there's anything else. So yeah, just remember when clear is asserted, when clear is high, output Q will be 0 no matter what. And yeah. And for state reduction, it's eliminating redundant states. It's 1. And then you can use an implication table. That. So, and then remember, when using Boolean algebra, oh, so you know what? I'm tired. It's 5 a.m. And